In a previous video, we have been looking at the concept of recursion. In this video, we'll explore some of the most important considerations when solving a problem recursively. In particular, we will be looking at the trade-off between simplicity of a recursive algorithm, the speed of execution, and the memory space needed to compute a solution. In order to do so, let's look at another well-known recursive function in mathematics, the Fibonacci sequence. Each number in the sequence is the sum of the two preceding ones, starting from 2. There are two base cases for n equals 0 or n equals 1. Fibonacci of 0 is equal to 0, and Fibonacci of 1 is equal to 1. The general case is written as Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2 for all n greater than 1. Let's look at a naive recursive implementation of the Fibonacci function. First, we should write the base cases. If n is equal to 0 or n is equal to 1, the answer will be n itself. For the general case, we compute the Fibonacci number using the previous two numbers. In other words, we need to return Fibonacci of n minus 1 plus Fibonacci of n minus 2. Let's check the correction of that implementation by printing the first 5 numbers of the Fibonacci sequence. We obtain the correct sequence 0, 1, 1, 2, and 3. You can admit that the recursive implementation is pretty easy, given the mathematical definition that was provided in the Fibonacci sequence. What about the efficiency of the implementation? Let's compute the first 30 numbers of the Fibonacci sequence. It's a little bit slow, but it's not too bad. Okay, let's go for 40 this time. It starts to slow down slightly, and it's getting slower and slower, and now it is very slow. We still don't have the completed sequence. We kind of hit a performance issue. Is it because computing such a sequence is a difficult problem, requiring massive resources? Or is it an implementation issue that renders the program useless? All recursive functions can be written in an iterative form. So, let's look at an iterative implementation of the Fibonacci sequence. Let's name it Fibonacci underscore iter to distinguish between this one from the recursive implementation. If n is equal to 0 or n is equal to 1, then I know I can return the value n. If n is greater or equal to 2, I need to build the sequence from 0 to n incrementally. To do so, I need to keep in memory the two previous numbers of the sequence, that is, Fibonacci of n minus 1 and Fibonacci of n minus 2. Let's store Fibonacci of n minus 1 into Fib1 and Fibonacci of n minus 2 into Fib2. We are going to build the sequence from the ground up using a for loop, starting with Fibonacci of 2 until we compute Fibonacci of n. For I, in range, starting from 2 because we already computed 0 and 1, and up to n included. Therefore, I need to put n plus 1 in the range function. After each iteration, Fibonacci of n minus 2 should receive the value of Fibonacci of n minus 1. And Fibonacci of n minus 1 should be updated to the newly computed value. I would recommend that you are trying to run the algorithm manually, so you have a better idea of what happens with Fib2 and Fib1. Once the for loop has terminated, the result is within Fib1, and I just need to return it. As you can see already, it can be a little bit more challenging to understand the iterative implementation given the mathematical definition of the Fibonacci sequence. It can be challenging to prove the correctness of the implementation as well. Now, I have two questions to answer. Does it produce the correct result? And does it perform better than the recursive implementation? The computation of the first 40 numbers in the Fibonacci sequence is almost instantaneous. So that's pretty quick compared to the recursive implementation. Why is that? To understand the issue, we should look at the recursion tree of the recursive implementation. The recursion tree represents all the function calls needed to complete the computation. In this example, we want to compute Fibonacci of 5. In order to complete this computation, we need to compute Fibonacci of 4 on the left branch, which needs to compute Fibonacci of 3, again on the left branch of the tree. And we keep doing that until we are at the end of the branch, which is one of the base case. Then we start looking at the right branch, the second term in the expression of the Fibonacci sequence. We keep doing that until we have our final result. Whilst going through all these function calls, we can see we are wasting resources, in this case, computation time. We had to compute twice Fibonacci of 3, 3 times Fibonacci of 2, and 5 times Fibonacci of 1. We repeat the same computation over and over. This is clearly inefficient. In fact, using the recursive implementation, around 2 at the power of n recursive calls are needed. That is more than 1 trillion calls to compute Fibonacci of 40. Compare that to the iterative implementation that only needs 40 iterations. Clearly, we need to pause and ask ourselves the following question. Does using recursion usually make your code faster? The answer is no. Does using recursion usually use less memory? Again, the answer is no. Then why use recursion? It sometimes makes your code much simpler. It is also easier to prove correctness of algorithm. In addition, there are techniques to improve the performance of recursive algorithms. Let's look at an implementation improving the performance of the Fibonacci function using recursion. Remember, we needed to compute many times the same Fibonacci number. If we could find a way to memorize this number that have already been computed, we will definitely improve the performance of our implementation. Let's implement the function Fibonacci _ mem, where mem is for memory. I need a convenience function in order to pass the previous computation into the parameters. That is my kind of memory of what I have done so far. Python allows us to define convenience function within a function definition. The parameter mem is my memory. I choose a dictionary to store my memory, where the keys are the indices already computed in the Fibonacci sequence, and the values are their corresponding Fibonacci numbers. If n is in mem, it means I have already computed that value. Then I just need to return the associated Fibonacci number, mem of n. I don't need any recursive call. This is my first base case. If n is equal to 0 or n is equal to 1, that's another base case. First, I must update the memory because this is the first time I'm computing them. So mem of n is equal to n itself. And then I can return mem of n. Finally, if the number is not already in memory, and it is not 0 or 1, then I need to compute it. Mem of n is equal to fib of n minus 1, and remember to pass the current memory as well. Plus fib of n minus 1, and again, I need to provide the memory of the computation I've done so far. Once computed, I return mem of n. Now that I've defined my convenience function, the next thing I need to do is calling the convenience function fib within the function Fibonacci underscore mem. Return the call of the local function fib with the parameter n, and because I didn't compute anything yet, the empty dictionary. Let's see if that implementation is faster than the previous recursive function. It is clear to see how much we have improved the performance of our implementation by using a form of memory. This technique is known as memorization. In case you wonder, the spelling is correct, nothing to do with my French accent. Although I improved dramatically the performance of my algorithm, there was a trade-off. I needed more memory to store the previously computed result. When looking at the complexity of algorithm, there will often be a trade-off between computation time and space in memory. In our example, I will need a little bit more memory space in order to gain a lot in computation time. In this example, there is also a need for a convenience function in order to keep the API clean. API meaning Application Public Interface. The user of our implementation should not know how we compute the result, only that it takes one parameter to compute the Fibonacci number. The convenience function, fib, inside the function Fibonacci underscore mem, hides the need for the additional parameter mem. This parameter is specific to the chosen implementation. I did not need that for the iterative implementation. In fact, the user of the function should not know if I used an iterative approach or if I have used a memorization. Every recursive function can be written as an iterative function. However, recursion is often simple and can be efficient, but it tends to be underutilized. Recursion is an elegant way to implement complex concepts. However, not all problems are suitable for a recursive implementation. If your problem can be written in terms of itself, that is decomposed into a similar subproblem with a, quote, smaller input, unquote, then a recursive approach may be suitable. It might even be easier to prove the correctness of the solution. Use recursion for clarity and sometimes for reduction in times needed to write or debug a code. However, you must be aware that recursion is not for space saving or speed of execution. A naive recursive implementation can become very computationally expensive. Thankfully, techniques exist to improve performance. Memorization is an example of such a technique. You should also remember that every recursive method must have at least one base case. That's the first rule. In addition, remember that every recursive method must make progress towards its base case. That's rule number 2. Some data structures, such as lists and trees, are recursive by nature. Many algorithms applied to this type of data structure are intrinsically recursive. Some of these data structures will be explored in a later video.